begin our eighth shape, the octahedral molecule. Again, this is a hypervalent case. In this particular instance, the central A is bonded outward to 6 singly bonded Bs. So it's sharing 12 pairs of electrons above the complete octet. So it's obviously involving some d orbitals in the so-called building of its connections to the 6 external Bs. There are going to be, in the octahedral case, no non-bonding pairs on the A, 6 single bonded cases outward. And despite the fact that the name is octahedral, the arrangement of them around there is not like a stop sign. What we have are 6 connected atoms, 4 in an equatorial plane that are 90 degrees apart. Then above that equatorial plane, there are 2 above and below, there are 2 axial arrangements of A to B. So there is a huge number of AB, BAB 90-degree bonds connecting first the 4 equatorial Bs in the center, and then 2 axial Bs above and below those central ones. There's a lot of symmetry, as we will see, to this shape, and it is also 3-dimensional because of the arrangement of all these Bs around the central A. Let's look how we will pictorially represent the octahedral molecule. Remember, it's AB6, and I have 6 single bonds outward from the central A to 6 Bs. Again, I mentioned equatorially, there are going to be 4 Bs that are 90 degrees perpendicular to one another. I'm representing those in the center here with a dash square. Now, you don't have to really draw the dash around those central ones. I'm just trying to do that for emphasis. I have this dash square in the middle of 4 90-degree bonds. I'm showing them in our attempt to represent them 3-dimensionally by having triangular bonds, 2 pointing with solid and 2 with hatches. The 2 solids are coming towards you, we'll say. The 2 hatches are sticking behind the page, we'll say. So there's a 90-degree arrangement in the middle for these equatorial ones. Then above and below that, there are axial ones connecting perpendicular to those 4 equatorial in the middle. All angles that you see are 90 degrees. Now, the reason this is termed an octahedral molecule, even though there are not 8 Bs attached to it, is that if you were to make this into a so-called platonic solid, it would have 8 sides to it. The picture at the bottom is attempting to represent that in a 2-dimensional way. The equatorial Bs you see in the center and the axial Bs are above and below. If you connected these Bs together and made the entity solid, it would have 8 faces, and it would have 8 equilateral triangle faces, a square pyramid above and a square pyramid below, connected together with 8 equilateral triangle faces. That is the nature and where the name octahedral comes from the number of faces a solid object with apices at the points of the Bs would be shaped if you connected them together. Our first example of an octahedral molecule, let's look at SF6. S is a column 16 element with 6 valence electrons. F, column 17, 7 valence electrons. Each of the 6 Fs needs to share an electron outward to the C, from the S to the F. So it will form 6 single bonds, SF single bonds from S to F. This makes the S in a hypervalent state of 12 electrons around it. And you see at the picture at the bottom how I would draw a cartoon representing the arrangement of those atoms around the central S. I put 4 fluorines in the center. the hatched and solid triangular bonds are representing single bonds from that S to those 4 equatorial Fs. Notice the 4 Fs in the equatorial positions each have 3 non-bonding or lone pairs of electrons around them. Then above that equatorial plane, I have an axial F above and an axial F below, 90 degrees apart from the equatorial Fs and 100 degrees apart from each other. Notice those 2 lines are thin, or are normal thickness of line, indicating those 2 Fs are on the plane page of the plane of the page. They're lying on the paper. So I have the axial Fs and the S lying on the paper. Then the solid bonds we'll say are the 2 Fs pointing out at me, 90 degrees apart, and then 90 degrees apart from that pointing to the back would be 2 Fs represented by the hatched bonds, so that this molecule is overall 3-dimensional. Another example of an octahedral molecule, let's look at GeH6 -2. So to do that, we'll take germanium, which is from column 14, which begins with 4 dots. We'll begin with an H from column 1, which has 1 dot. Of course, the H does not want a complete octet, but it does want 2 electrons around it to complete the 1s orbital in row 1. The Ge will have, as we see there, it's going to connect 6 of those H's in single bonds, but it can't do so unless it has 6 electrons. So because this is a -2 anion, the 2 electrons, as we've described before, I will place onto the central Ge. So then those 6 electrons around the central Ge will singly bond outward to 6 H's. 4 of those H's will end up in equatorial positions represented by the the solid and hatched triangular bonds that you see here, 2 of which pointing towards you, 2 of which pointing behind the page. Then above and below those that equatorial set will be 2 additional H's, single bonded, as you see by the thin lines representing axial hydrogens. Remember, the correct way to do this includes the fact that I enclose the entire anion in brackets and I put the total charge on the outside as chemistry convention shows, and this would be how I would build that octahedral molecule. To our 9th shape, which is now going to be based upon the trigonal bipyramid shape that we saw as shape number 7. What we're going to do now is begin to remove bond pairs from the trigonal bipyramid and replace the bond pairs with non-bond pairs. So the first of those cases will be what we call a distorted tetrahedron, and how that arises is I begin with AB5, which has 5 single bonded B's to A, and I remove one of the B's so that there are 4 B's remaining, but there is a non-bonding lone pair of electrons on the central A. And those 4 bond pairs plus the 1 non-bonding pair still give a total of 10 valence electrons on the central A. So unlike the AB4 with no non-bonding pairs, these bond pairs are going to, with no non-bonding pairs, this non-bonding pair in addition to the 4 bond pairs is going to shove the 4 B bonds to other than tetrahedral arrangement. Okay, so remember the basic shape of the trigonal bipyramid. I had 3 axial B's in a 120 degree equatorial triangle. Then I had 2, I said that wrong again and I apologize. I have 3 equatorial B's around the 120 degree equilateral triangle in the middle of the molecule. And above and below that I have 2 axial B's, 90 degrees above and below. Now what has been determined experimentally is that when you make these hypervalent cases where the central atom has non-bonding pairs of electrons. Then for the trigonal bipyramid cases, you always place the non-bonding pair of electrons into the equatorial positions or into the triangle. Now again, this is known from experimental rendering of the geometry of the molecules that the bonding bees are always that remain such that non-bonding electrons are in the triangle. So for all trigonal bipyramid based molecules which have lone pairs of electrons, the lone pairs are always going to go into the equatorial positions. So when you pop one bond pair from the equatorial position and replace it with a non-bond pair, the remaining 4 B's look distorted as a tetrahedron. A regular tetrahedron would have 109.5 degree angles. This distorted tetrahedron has weird angles, and they're so weird that I am not really going to require that you know what those angles would be directly. It really varies depending on what the central atom is and also what the attaching atoms are. Let's look at how we will pictorially represent a distorted tetrahedron molecule. We begin with the shape of the trigonal bipyramid, where there are 3 so-called equatorial positions arranged in an equilateral triangle with 2 axial positions above and below. As prescription requires, we will remove one of the equatorial bond pairs and put on a non-bond pair. I'm showing essentially maybe a picture you might not like too much there. I'm showing a bond to a non-bond pair of electrons, but for clarity I thought this would be the best way to represent that picture. There's a connection to the non-bonding pair of electrons in one of the equatorial locations, as you can see there. So there really isn't a bond to the non-bonding electrons, but we're just saying that the dots are taking up the position of one of the B's. Remember, the nuclei are the big bulky things, the electrons are not. So the look or geometry of the molecule is dictated by the B's and not by the dots. So then after I put one of the bonded B's or remove one of the bonded B's and put a pair of dots in its location, the remaining 4 B's are not tetrahedrally distributed around the A because of the presence of that non-bonding pair. Remember, it's repulsive, and as a matter of fact, more repulsive than the bond pairs. So it starts pushing on those other 4 bond pairs, and the locations to where they are pushed are best described as a distorted tetrahedron. Now, if I turn that sideways, now remember, this still is a 3-dimensional molecule because the thick triangular and hatched triangular bonds indicate coming towards you and away from you. So there's a BAB thin bond representing those B's, and that central A are on the page. Then there's a B pointing towards you and a B pointing away from you. As a matter of fact, the dots in this representation are also on the page as well. So this would be an arrangement that is still 3-dimensional in nature. If I turn my distorted tetrahedral molecule sideways and put the incoming and outgoing B's at the bottom, they create like a balancing fulcrum point where I have the A sitting right on top of them, and I have 2 B's out from them, as if this is a seesaw. So sometimes this molecule is referred to, instead of being a distorted tetrahedron, sometimes this molecule is referred to as being a seesaw molecule. Example of a distorted tetrahedral molecule. Let's look at xenon tetrahydride +2. Okay, so this is a cation using xenon as the central atom. Remember, first of all, xenon is one of our noble gas, or column 18 elements. And we talked about the fact that these are not very reactive. Well, what I would claim to you is if you work hard enough, put enough energy into the situation, you can force anything to do anything you want in chemistry. So somebody worked very hard to force the xenon into a reactive state. So this is probably a highly energetic reaction in order to form this product, but be that as it may, I begin with a xenon in the central, which is a column 18 complete octet atom. That's why it really doesn't want to react. But somehow I doubly ionize that. I remove 2 electrons from it. So that leaves 6 electrons left on the xenon. Then I attach 4 hydrogens in single bonds. So 4 of the remaining 6 electrons are taken up by single bonds. Then after that is done, and since it's doubly ionized, there are still 2 remaining non-bonding electrons. So there's a lone pair and 4 bond pairs on the xenon tetrahydride. So what I do with these 5 sets of electrons, remember, this is still hypervalent because there are 10 electrons around the xenon after it's been doubly ionized, and there are 4 shared single electrons with hydrogens outward. So there's 10 electrons around xenon. Those 10 electron pairs spread as far apart as they could. If they were all bond pairs, they would go completely perfectly trigonal bipyramid. But since there are 4 bond pairs and 1 non-bond pair, one of the locations of the equatorial bonds is replaced by a non-bond lone pair. Now in this picture, what you see is I did not draw a line to that bond. A little more correctly, maybe, if you think about it. It's not a bond to the non-bonding pairs. So I just put the non-bonding pair in the third location of the equatorial triangle of bonds in the middle. And there are 4 remaining bonds, 2 in the equatorial positions, 2 in the axial positions. And as decorum requires, I group the entire molecule in parentheses and put the total charge on the outside. So this molecule has the distorted tetrahedral appearance. Go to our 10th shape, the so-called T-shaped molecule. Once again, it is based on the beginning point of the trigonal bipyramid. Trigonal bipyramid is a hypervalent molecule with 10 electrons on the central A. In the T-shaped case, you still have 10 electrons on the central A, but in this instance, you have 3 sets of bond pairs, or 3 Bs attached to the central A, and you have 2 non-bonding lone pairs of electrons on the central A. Now, as we did in the case of the distorted tetrahedron, the non-bonding pairs of electrons are located in the equatorial triangular positions in the middle of the trigonal bipyramid. So I essentially am popping 2 Bs loose from the triangle in the middle, or in the equatorial positions. There's 1 equatorial B remaining. Then the axial Bs above and below that plane also remain. So these things are 90 degrees apart. The remaining equatorial B is 90 degrees from either of the 2 axial Bs above and below. Now, because of the nature of this, as we will see on the next slide, even though the trigonal bipyramid begins as being 3-dimensional, when we pop those 2 Bs off of the equatorial positions, the remaining 3 Bs can be arranged in the same plane so that the T-shaped molecule is 2-dimensional. So we'll take a look at how that comes about in upcoming slides. Some cartoon representations of the T-shaped molecule. Again, I begin with a trigonal bipyramid with 3 equatorial Bs and 2 axial Bs. As experimental evidence shows, the B's which are removed and replaced by non-bonding pairs of electrons in this 10 valence electron case, the non-bonding pair of electrons go in the equatorial positions that you see I'm drawing there. So there's one remaining equatorial B, and then there are two axial B's above and below that plane. Notice by placing the non-bonding pair of electrons onto the solid and hatched triangular bonds, indicating they're coming toward me and going behind the paper. The remaining three B's can be represented by thin line bonds, or indicating that they are in the same plane, flat on the page, along with the A. So the T-shaped molecule is two-dimensional, all B's and A's lying in the same plane, here the paper. Now if I turn this sideways, and again so that now the non-bonding pairs of electrons are one set coming toward me, one set going behind the paper, then the remaining three B's and A form the shape of a T, hence the nature of the name T-shaped molecule. Let's look at a T-shape example. We'll take ClF3, chlorine tetrafluoride. Both Cl and F are column 17 elements, and there would then be, if you want the total, there'd be 4 times 7 or 28 total valence electrons between the atoms. And what happens is, of course, the fluorine need another electron, so they will single bond and share with chlorine. So 3 of the chlorine electrons are shared in single bonds with fluorine, and then there are 3 bond pairs on the chlorine and 4 remaining electrons, which form 2 non-bonding pairs of electrons. The 2 non-bonding pairs are placed in equatorial positions. That leaves one F in the equatorial position and 2 F's in axial positions. I can locate those on the skinny bonds, indicating they're all in the same plane. And the non-bonding pairs of electrons are coming towards you and going behind the paper. Notice I also have dots representing the non-bonding pairs of electrons on the central F. Let's turn to our 11th shape. This one will be called the linear number 2. Once again, it is based on the trigonal bipyramid. We saw a trigonal bipyramid with no non-bonding pairs of electrons, has 5 B's attached to it, 3 equatorial B's and 2 axial B's above and below that plane. Then we had an AB4 with 1 non-bonding pair based on the trigonal bipyramid, which puts a non-bonding pair in the equatorial position, leaving the 4 remaining B's in the so-called distorted tetrahedron. Last slide we just showed was when you had 2 non-bonding pairs on the central A, putting both of those non-bonding pairs in the equatorial positions left an AB3 molecule. Now we are going to take 3 non-bonding pairs of electrons, place all those non-bonding pairs in the equatorial positions, leaving behind only the axial B's. And those 2 B's are, of course, 180 degrees apart from one another. Now, for lack of a better way to call this molecule, if you have an AB2 that has 3 non-bonding pairs, we're going to call it linear number 2. Now, notice this is still what we would term a hypervalent molecule. It is hypervalent because among the 3 non-bonding pairs, that's 6 electrons. You have 2 bonding single bond pairs to 2 axial B's. That's 4 more electrons. So we have 6 plus 4, or 10 electrons, which goes beyond a complete octet. Look at our pictorial representation of the linear number 2 molecule. We again begin with the trigonal bipyramid case, and we'll note that the A in the middle is hypervalent with a total of 10 valence electrons around it. Now what we do in the case of the linear number 2 is we form two bond pairs outward to the axial B locations. Notice thin line bonds, meaning all these atoms B, A, and B are in the straight line. Notice they are 180 degrees apart from one another. The three non-bonding lone pairs of electrons are placed in the so-called equatorial positions. They get 120 degrees apart from one another. This kind of maximizes the distance of the non-bond pairs from each other. If you put one in the axial position and a couple in the non-axial positions, they would be 90 degrees apart from one another. So by putting them all equatorial, they can get further apart, all being 120 degrees from one another. So remembering again that the actual shape is defined by the much more massive nuclei. So the BAB positions are really what you see from a distance because of the tininess of the electrons. So what you see is a linear arrangement of the nuclei when you have these non-bonding electrons in equatorial positions. An example of a linear number 2 molecule. Let's take I3, that is an anion of -1 charge. So it's a connection of 3 iodines, which I'm going to put together and bond one in the middle and two outwardly from that. And each iodine begins with 7 valence electrons, so that's 21 total for them. But because it's I3 minus 1, I will have 22 total valence electrons when I add one to the central I. So I'll start with the central I with already 8 electrons around it. I will let it singly bond outward to 2 I's external to that. So it'll form a single bond to the 2 I's outward, using up 2 of those 8 electrons around the central I. There are 6 electrons remaining. They form 3 non-bonding pairs that all arrange equatorially, around the central equilateral triangle. They get 120 degrees apart in the middle, and they take up the positions that you see in the picture below. Then axial to that, we have 2 singly bonded I's with thin lines indicating all 3 I's lie in the straight line. And notice the external I's have representations of their non-bonding electrons shown with lines as you see there. The remaining 2 shapes will be derived from the starting point of the hypervalent octahedral molecule, which had 12 valence electrons around the central A. The first of which we'll call shape 12, which I will describe as being a square pyramid molecule. A square pyramid molecule has the general form AB5, just like a trigonal bipyramid. However, in this particular case, the central A does not have only bond pairs as the trigonal bipyramid does. Here, the central A also contains 1 lone pair of non-bonding electrons. So that means there are still 12 electrons around the central A. Those 12 electrons would be in 6 pairs that, if they were all bond pairs, would be octahedral. And remember, those are a set of 90-degree bond angles between 4 equatorial B's in the center, and then a B above and a B below, so that everything was 90 degrees. Here, in this particular case, where I'm having my hypervalent molecule, where I removed one of the B's, first of all, it really doesn't matter, at least on this particular case for shape 12, which B I remove. Remember, we were very literal and distinct in the previous 3 hypervalent cases where there were non-bonding pairs in the trigonal bipyramid. You had to remove the B from the equatorial position. Here in the octahedron, all positions are exactly equivalent, meaning by flipping the molecule over, any of the B's can be placed in the equatorial location. So there really is no defining equatorial point at the outset of an octahedron. I can literally pop any of the B's off because any of them could be axial, any of them could be equatorial, depending on how I rotate the molecule. So once I pop one of those B's off, though, what I'm going to claim is I'm going to rotate the molecule around so that the B I popped off was the axial B on the bottom. Then I have 4 remaining equatorial B's and 1 axial B above that equatorial plane. Now, if you were to connect these together and make it a solid shape, it would look like a square-based pyramid. Hence the nature of the name, square pyramid. Look at a graphical representation of the square pyramid molecule. Again, remember, this is based on an octahedron, which should have 6 equivalent bond locations. But this will be an AB5 molecule with a single lone pair. Let's just state I take the lone pair from the bottom axial B, and I take the bond away from the axial bottom B, stick a non-bond pair on there. Now I'm drawing a line to that non-bonding pair, which technically should not be there really. There's not a bond to the non-bonding pair, but just for emphasis of the octahedron, I'm showing that position is where the non-bonding pair goes. I still have the 4 remaining equatorial B's, and then I have a single axial B above that. If you were to connect this into a solid, a platonic solid kind of thing, I would have a square-based pyramid like the pyramids in Egypt, and then I would have 4 faces, each being an equilateral triangle, forming the so-called square pyramid. For an example of the square pyramid case, let's take krypton pentahydride. That is a +1 cation. Krypton, again, is a column 18 element like the xenon I used in a previous example. Column 18 elements already have a completed octet. They really don't want to be very reactive. I have to force this to react by using lots of energetics probably. But somehow, let's say I ionize the krypton to a +1 state, making it have 7 valence electrons. Then I attach 5 hydrogens in single bonds to 5 of those valence electrons. There are 2 valence electrons left, so I have 5 bond pairs and 1 lone pair. So this would be a total of 6 pairs of electrons around the krypton. And what happens is I begin then with an octahedron. I take the position of the axial B at the bottom of the octahedron away, replace it with a non-bonding pair that you see I show in the picture without a line. Then I have my 4 equatorial B's such that they are 90 degrees apart. And that's a 3-dimensional section of the molecule. So 2 of those H's are pointing toward me. 2 of those H's are going behind the page. Then I have 1 remaining axial H above those 4 equatorial ones. So I have an overall 3-dimensional molecule of a square pyramid. I enclose the entire thing in brackets as I'm supposed to do and put the total charge on the outside. Last shape will be the square planar molecule. It is again derived from the octahedral case. The octahedral case is the hypervalent situation where there are 12 electrons around the central A. So this begins with 12 electrons around the central A. But in this instance, there are 4 bond pairs, since I have 4 B's attached to it, 4 single bonded B's. Then I have 2 sets of non-bonding pairs on that central A. Now, because of the high repulsiveness of these, those non-bonding pairs will not be 90 degrees opposed to one another. They will try to, the lone pairs will get as far apart as they can, so they will get 180 degrees apart from one another. So when I do this, the best way of thinking of it is to take my beginning octahedron, leave all the equatorial B's alone and place the non-bonding electrons at the B positions that were axial in the octahedron. So the remaining 4 are in the equatorial positions, 90 degrees apart from one another. They form a square, and all 4 of these atoms can be lie flat on the same plane. So this is square planar. A pictorial representation of square pyramid begins with the octahedral arrangement. There would be, of course, 6 attachments to the central A in the octahedron. I leave the 4 B's that are in the equatorial locations alone. And then axial to those 4 B's, I put the 2 sets of non-bonding electrons. Now, it might not seem like it from this orientation that I'm showing here, but all the remaining B's that are 90 degrees opposed to one another with the A can all be placed in the same plane. Hence the nature of the name, square planar molecule. Later I'll show a little picture where I do demonstrate the square planar nature of this when I show you with some models after we're done with all the structures. For our square planar example, I will use xenon tetrabromide. Again, xenon is a column 18 element with a complete octet already, really technically not very reactive. This is not a cation or an anion, so I don't remove any electrons, but I will singly bond 4 bromines to the xenon, so 4 of its electrons are shared outward as bromine shares 1 back, making 4 single bonds. In addition, there are 2 remaining non-bonding pairs of electrons. These 6 sets of electrons around the central xenon are arranged as shown at the bottom. The axial positions are taken up with non-bonding lone pairs. I don't draw the lines. As you see, I just put the dots above and below. And then the bromines are in the equatorial positions with single bonds represented by the solid triangular bonds and the hatched triangular bonds, 2 coming toward me, 2 going away from me. Again, maybe it does not look so, but maybe a little later I will show you a representation how these are all planar to one another. Remember, I do not forget the non-bonding pairs of electrons on the bromine when I'm drawing the correct Lewis-Dot structure of xenon tetrabromide. This slide represents a summary of the VSEPR geometries that we're supposed to be aware of. Now, if I have B's connected to A's, those are bonded atoms connected to A. If I have E in these representations, that means non-bonding lone pair of electrons. So we would begin on the far left with 1, 2, 3, 4, 5 basic shapes: linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. Each of these 5 basic shapes has no non-bonding pairs on the central atom, only bond pairs, as indicated by AB2, AB3, AB4, AB5, AB6. Down there's no E in the representation. Now, when you go to the second column, there's a single non-bonding pair in each case except the linear case. For the trigonal planar, the tetrahedral, trigonal bipyramid, or octahedral, we discussed a 1 lone pair of electron case for each of those. So derived from the trigonal planar, I have the AB2E, which means 2 of the trigonal planar locations are bonded atoms. Then there's a non-bonding pair of electrons on the third. I have an AB3E from the tetrahedron, 3 bonded atoms and 1 lone pair. I have an AB4E starting from the trigonal bipyramid, and I have an AB5E starting from the octahedral. When I do these for the trigonal planar case, when I take off one of the B's and put on pair, I get a bent molecule. For the tetrahedral case, when I take off a B and put on a pair of electrons, I get the trigonal pyramid. For the trigonal bipyramid starting point, by taking off one of the B's, I end up with the so-called distorted tetrahedron. For the octahedral case, when I take off one of the B's, I end up with the so-called square pyramid. There are three cases which we discussed where there are two non-bonding pairs of electrons possible on the central atom. We discussed those for the tetrahedral, trigonal bipyramid, and octahedral cases, leading to the so-called really bent, T-shaped, and square planar molecules, as you see in the third column. Then finally, for the fourth column, we only talked about one of the shapes that we could envision with three non-bonding pairs. We didn't do so for the octahedron, but we did do so for the trigonal bipyramid. That resulted in the shape we know as linear number 2. I thought I'd get up close and personal and show you a few of these models with my little kit that you can order online, a bunch of molecular modeling kits. Here I show my linear molecule. Now in the linear case, of course we have several different AB2 molecules. This is AB2. There's no non-bonding pairs of electrons on the central A, and there are two yellow balls representing B molecules that you see out to the left and right, and these plastic gray entities indicate I have double bonding from the central A out to this B. I have double bonding from the central A out to this B. Now these bonding pairs push as far apart as they can, and they get 180 degrees apart from one another. Then I have this particular arrangement, which I call trigonal planar. Notice that when I hold this flat out like this, it's nice and flat looking. At least the black spheres all appear in the same plane. This is my central A bonded to 3 external B's. There's a double bond to one of the B's from the central A. There are single bonds from the other 2 B's to A. So there's 3 bond pairs, no lone pairs. The pairs push as far apart as they can. This is a 120 degree angle. This is a 120 degree angle. This is a 120 degree angle. So I have my AB3, no lone pairs, trigonal planar arrangement of the atoms. Okay, then I come to this case. Now notice when I go from AB3 to AB4, I am now making a so-called 3-dimensional molecule. Notice the AB3 molecule is flat. The AB4 molecule takes up 3 dimensions of space. I have single bonds from the central A out to the 4 red B's. There's a complete octet on the central A. And now notice, interestingly, this is 109.5 degrees. This is 109.5 degrees. This angle creates 109.5 degrees. All angles around this central A in all dimensions of space, all are equivalent and all are 109.5 degrees, because that's the maximum distance you can repel between the pairs so that they can get as far apart as possible. Now if I go to my hypervalent cases, the first of which is what I would call the trigonal bipyramid looking molecule, and the trigonal bipyramid is AB5. Remember, there are no non-bonding pairs on the black A sphere. The white spheres are the B's. There are 5 of them attached by single bonds. This is hypervalent because A has 10 valence electrons that are touching it. So this is involving d orbitals in some way above the complete octet. Now let's look at the arrangement of them. There's a 120 degree angle triangle in the middle of the molecule. So in the middle here are 3 B's all spread apart by 120 degrees. Above that plane of 120 degree B's, there's a 90 degree perpendicular B. Below the plane, there's a 90 degree perpendicular B. So again, 120, 120, 120, above and below 90. So these are the equatorial B's that create the triangle in the middle, and these are the axial B's, above and below. I'll hold on the equatorial ones. These are the axial ones, above and below that equatorial plane. Then finally, I have the AB6 molecule. It is also hypervalent. The A in the middle, represented by the silver sphere, has 6 attachments to it, 6 shared pairs of electrons. That's a total of 12 valence electrons on that central silver sphere. So it is using some sort of d orbitals involving, so it's beyond a complete octet. Single bonds outward to the other elements. I have now 90 degree 4 B's in the center. You can see I got a square of them in the middle. Then above and below that square, perpendicular above, perpendicular below, I have another 2 B's bonded to the central A. So again, in the middle, I have a square of 90 degree B's. Those are the equatorial B's. Above and below, I have 2 axial B's. Now notice the high degree of symmetry in the AB6 arrangement. As soon as I turn the molecule, flip it 90 degrees, I've defined 4 new equatorial B's and 2 new axial B's. So I get 2 axial B's there and 4 in the center. Flip it again, 4 equatorial B's, 2 above and below. Okay, now, if we go back, say, to our trigonal pyramid arrangement, and instead of having no lone pairs on the central A, let me take one of the B's loose and let me connect instead a representation of non-bonding pairs of electrons. This little lobe here represents no electrons bonded to the central atom. I'm sorry, no B bonded to the central atom, just electrons there. So this is a lone pair of electrons. Now I have a remaining double bond and a remaining single bond. So the central A still has a complete octet, but now in the position where there was a B bonded, I have a non-bonding pair of electrons, and the shape is defined by the centers. So I have 3 remaining centers that would have been in trigonal planar locations, but now because of the removal of one of the B's, they are in what we call the bent position. The angle between the B's to the central A would be pushed down by this non-bonding pair, and so the angle between the B's to the A's is somewhat less than 120 degrees, as we discussed. Okay, now I'm going to go to my tetrahedral arrangement. Remember, this is 3-dimensional. All the angles are 109.5 degrees. And instead of having an AB4 with no lone pairs on the A, let's suppose I take one of the B's away, and instead I replace it with a non-bonding pair of electrons. Notice how the remaining 3 B's take up the remaining positions of the tetrahedron, and those remaining positions are 3-dimensional. Now, what should occur is if this was a perfect tetrahedron, all angles would be 109.5, but because of the presence of the non-bonding pair of electrons, these angles down here are pushed to less than 109.5 degrees. So I have an AB3 molecule that has bond angles less than 109.5 when I have the trigonal pyramid arrangement. Okay, now next what I'm going to do is pop another pair of electrons loose from the tetrahedron, put a non-bonding pair on there, and what I have left are AB2 with two non-bonding pairs. Notice the non-bonding pairs form a plane with the central A, and the bond pairs form a plane with the central A. The B's are flat compared to where the non-bonding pairs are. I have a non-bonding pair above, I have a non-bonding pair below, but the BAB form a plane. So remember, molecules of AB2 form with two non-bonding pairs of electron are two-dimensional, even though they originate from a three-dimensional structure. So again, an AB2 with two lone pairs is a really bent molecule, and I call it really bent to contrast from bent because the bent is such that the lone pairs push the bond angle to less than 120. The really bent push the bond angles to less than 109.5 degrees. Okay, now if I turn to my so-called hypervalent cases, I can begin with the trigonal bipyramid. Remember, the trigonal bipyramid is a unique one that has starting with different bond angles. All the other ones start with the same bond angles. So I have three 120-degree angles in the AB5 molecule, two 90-degree angle for the axial ones that are above and below the plane of the ring in the center. Okay, so now if I begin to pop off atoms from the AB5 arrangement, as we discussed in the slides previously, you pop electrons, or bond pairs from the equatorial positions. How do we know this? Experimentally, that's what we see for the shapes of these molecules. The electrons that pop off come out of the center here. So I will pop off one, and I will place a lone pair in its place, and then what I have is a so-called distorted tetrahedron. I have four remaining B's, but they are not at 109.5 degrees from one another. As a matter of fact, they're weird angles, and the angles are so weird, I'm not going to prefer that you really know those angles. So I have a non-bonding pair on the central A, four single bond pairs. It's still hypervalent, yet I don't have those bonds arranged at 109 or less than or equal to exactly 109.5 as they would if this is a pure tetrahedron. Now I also said this is kind of like a seesaw molecule because I can use these two B's as the fulcrum, and then I can rock the molecule relative to the remaining two B's. All right, now if I pop a second B from the original axial position, put a non-bond pair in the place of the second B, the remaining three B's are planar to the central A, and the angles are again 90 degrees apart. Notice how the non-bond pairs form the out of plane locations. The bond pairs are in plane locations. We called this the T-shape molecule, obviously, because of the three 90-degree bonds. Again, the non-bonding lone pairs of electrons go in the axial positions, and so I remain, scratch that, the non-bond pairs of electrons go in the equatorial positions, The two axial positions remain, and one equatorial position remains, and they look like a T. Now, I can also have the case of three lone pairs on the central A, and again, that comes from the equatorial positions, and when I do so, I have this remaining point. I put all non-bond pairs equatorial, and I put the bond pairs axial to them, and now the molecule is linear. And for lack of a better name, I call this linear number 2. So linear number 2 has two bond pairs and three non-bonding pairs on the central A. That gives it a hypervalent case of 10 electrons on the central A, but the bond angle again becomes 180 degrees because of the push. Now, the T-shaped molecule and the linear molecule, of course, are planar arrangements, but they begin from the non-planar three-dimensional AB5 trigonal bipyramid molecule. Now, let me again notice for you that I have three possibilities of my linear cases. Here's an AB2 with no lone pairs on the central A. Then the two bond pairs are 180 degrees apart. That's linear. I have an AB2 with one lone pair on the central A. And in a case like that, because it begins as a trigonal planar molecule, they want to be 120 degrees apart, but the non-bonding pair makes that angle less than 120. Then I have my AB2 with two lone pairs on the central A. That again is linear, as all AB2 molecules must be. And now the non-bonding pairs or lone pairs are out of plane with the bond pairs, as you see, because this begins as the tetrahedral case. So I go from 180 down to less than 120 in the bent case, down to less than 109.5 when I have two lone pairs on the central A for the case of the really bent molecule. Then I return with three lone pairs on the central A. So I can have a AB2 molecule with no lone pairs, an AB2 molecule with one, an AB2 molecule with two, and now we see an AB2 molecule with three lone pairs. And that is what I'm going to call linear number two, for lack of a better name. All right, and then finally, I can begin with my hypervalent AB6 octahedral case. We will look at two hypervalent cases that stem from this, where I have lone pairs on the central A instead of 6 bond pairs. Now I can remove an A. Now literally here, these are all equivalent. It doesn't really define which is equatorial and which is axial because of the arrangement around here. So I'm just going to take this particular one off and put a non-bond pair on that position. And the remaining ones are what I called square pyramid. I have the four in the so-called equatorial locations, as you can see. Then I have one perpendicular to those equatorial positions, and this is shaped like the pyramids in Gaza, as opposed to a trigonal pyramid, which has a triangle at its base. This is a square pyramid, which has a square at its base. So an AB5 with one lone pair we call a square pyramid molecule. Now then I can have an AB4 with two lone pairs, but now specifically because of the repulsiveness of those lone pairs, the second lone pair has to be as far away from the first as possible, so it will go at the other axial position. So I have four remaining equatorial B's in the same plane as the A. Now remember, an AB6 or octahedral molecule is three-dimensional. An AB5 or square pyramid molecule is three-dimensional. But now a square planar molecule, as the name implies, is a two-dimensional square molecule where all the atoms are in the same plane. So that's our tour of the various shapes. And I, of course, want you to know all the nuanced, detailed information about each one of these. Let's talk a little bit about the geometry of organic molecules. And this becomes really important when you start to look at the geometry of biomolecules, which are based on carbon backbones from the organic world, because the structure and function and behavior of many of these proteins and enzymes and things of that sort are distinctly related to how they are shaped. So carbon, as we remember, is the basis of organic molecules because of the great ability of carbon to bind to itself over and over again, because of its small size and perfect number of valence electrons. It's conducive to carbon bonding not only to itself, but to many other elements, including hydrogen, nitrogen, oxygen. Those are mostly the ones in organic cases anyways. Another very important thing about carbon is that it really does not like non-bonding pairs of electrons. It likes to have all bond pairs. And also that carbon distinctly is celebrated for its ability to not only single bond to itself and other elements, it can double bond to itself and other elements, as well as triple bond to itself and other elements. So let's talk a little bit about what ends up to be the geometry of carbon-based molecules as they go through single bonding to themselves, double bonding to themselves, and triple bonding to themselves. When a carbon single bonds to itself, since it began with 4 valence electrons, or if it single bonds, not only to itself, but to all other entities that it is bonding with, it will form 4 single bonds. Then Vespers says that you repel those 4 single bonds to the maximum distance between each other. That will make a tetrahedral arrangement for all single bonded carbon cases. Now this is true when there's a single carbon center, as we see in the top left, for methane, the simplest of all possible hydrocarbons. Now if I pop an H off of 2 methanes, slide them together on that remaining bond, I can make ethane, which is the middle top picture, where I'm showing 2 concatenated tetrahedra, indicated by the thin bonds being on the page, plane of the page of the paper. The hatched and solid triangular bonds are either coming out or going behind the paper. So ethane is 2 concatenated tetrahedra. If I go to propane, that is 3 concatenated tetrahedra. As you see, I can do butane, which is 4 concatenated tetrahedra, pentane, hexane, octane, and on it goes. The nomenclature hierarchy is so that the ANE ending means all single bonded carbons, and the prefix tells you the number of carbons in that chain. So all these ANE ending molecules are tetrahedral arrangements around the central carbon, concatenated tetrahedra for multiple connections. Let's move now to doubly bonded carbons. If I double bond the carbons together with no non-bonding pairs of electrons, then I have 2 remaining single bonds that the carbons can undertake. I can have what I call ethene. Again, notice the F prefix, just like shown above, means 2 carbons connected, but the ene ending means, instead of like ane, where they're single bonded carbons, and the ene ending, they're double bonded carbons. So ethene has 2 carbons that are double bonding and single bonding relative to one another. That is a trigonal planar arrangement around the C's. Notice all the bonds are thin now, meaning they're all lying on the page, and I would have 120-degree angles between all atoms you see in ethene. The same thing is true as I continue this idea. I can't do that same kind of connection if I make a 2 carbon double bond propene, but I can do so with a 2 carbon double bond butte-based molecule or 4 carbon-based molecule. I'm showing 1,3-butadiene. The name has a lot of meaning to it. 1 and 3 tell the locations of the double bonds. Bute means 4 carbons in the chain, and diene means 2 double bonds. So you see I arrange essentially 4 concatenated trigonal planar arrangements. This is a flat molecule. All the atoms lie on the page, as indicated by the thickness of the lines. So around each carbon is a trigonal planar arrangement around that position. Then for a triple bonded carbon collection, what I can do is, of course, after carbon triple bonds, sharing 3 electrons outward with another carbon, that's 6 electrons involved in the triple bond. There's 1 remaining valence electron on each carbon atom. which single bonds outward from that point. So in the case when carbon is triple bonding, in order to complete its octet, it has one remaining single bond as well, and this triple and single bond push as far apart from one another as they can so that they get linear. So F-ine and the Y-N-E ending is now indicating F for two carbons, ine for triple bond between them, and they get 180 degrees apart in a linear arrangement as you see in the bottom left picture. The bottom right picture is 1,3-butadiene. Again, a lot of information given in the name. 1 and 3 tells you the double bonding locations. But tells you 4 carbons in the chain. Diene tells me 2 double bonds located at those 1 and 3 positions. All carbons and hydrogens get 180 degrees apart from one another in that case, and they form a linear arrangement around that. Now I can substitute these chains with other groups like trigonal planar, other groups of oxygen, and maybe not oxygen wouldn't do that, but nitrogen might do that or things of that sort. I can put trigonal pyramid groups attached to this chain. I could put really bent groups attached to this chain, so I can really vary the geometry of the carbon-carbon chain dramatically by the local Vesper geometry around each center. Briefly about the geometry of ring-shaped molecules of organic in the organic world. I can concatenate 6 tetrahedra together, but instead of having them in a straight line, I connect carbon 1 to carbon 6 and have 6 concatenated ring tetrahedra in what I call cyclohexane. Of course, the ane ending means single bonds. Cyclo means in a ring. Hex means 6 carbons. The special case of 6 carbons where they alternate single and double bonds is given a special name, and that is called benzene due to its traditional use in chemistry before its structure was understood. Benzene is 6 concatenated trigonal planar carbon atoms. There's a single bond or 2 single bonds and 1 double bond attached to each, no non-bonding pairs. Those 3 bonding pairs around each carbon get 120 degrees apart, and that is done so by forming the trigonal planar geometry. If you hold benzene on its side, all atoms are in the same plane, and all angles in the benzene molecule are 120 degrees apart. I can begin to concatenate these, making what I call polycyclic aromatics, polycyclic aromatic hydrocarbons in particular, where I have connections of a huge number of atoms, kind of forming a chicken wire structure, all being in trigonal planar arrangements around one another. Introduce some examples where I functionalize the hydrocarbon, which means I attach atoms other than carbon to the carbon-carbon backbone. Now these other atoms which I attach now open the possibility of adding in geometric features other than the ones shown for carbon and hydrogen bonding, which were tetrahedral, trigonal planar, and linear cases. In things like what I show in the top picture, which is known as ethanol, or I'm sorry, that's methanol, excuse me. It has a methane attached to an alcohol group. The alcohol group is OH attached to the methane group, which is CH3. Now around the carbon, you'll note I have 4 attachments, and they are arranged so that they're looking tetrahedral. There's 2 H's coming in and out of the plane, as you note, and there are 2 CH and a CO bond in the plane that we note there. So the arrangement around the left C in methanol is tetrahedral. Then I have a C bonded to single bonded to O. That O has 2 non-bonding pairs of electrons on it, and then it single bonds to an H. Around that O all those pairs of electrons were placed in space, they would try to get tetrahedral as well. They get those four pairs of electrons get as far apart as they can, which would try to be tetrahedral. Two of the points of the tetrahedron are taken up by the non-bonding pairs. The remaining two are taken up by the bond pairs. So I notice I draw the bonding lines from the O to the C and the O to the H with a thin line indicating they're on the page. Then the two sets of dots should really be in locations sticking above, out of the page, and behind the page, so that that section of the molecule is flat. Notice in the middle I show formaldehyde, which has a carbon doubly bonding to an oxygen and two hydrogens. There's a trigonal planar arrangement around that connection as well. Then I show on the bottom right the molecule called pyrrole, where a nitrogen is in the ring, and you should be able to recognize what kind of geometry that nitrogen is using. First of all, the remaining 5 carbons are using trigonal planar geometry. How do I know that? Because there are no non-bonding pairs represented in the picture of it, all bond pairs. There are 3 bond pairs on each carbon. Those get as far apart as they can. That'll be trigonal planar. But if you look at the nitrogen in the pyrrole molecule, it has a double bond to one C, a single bond to the other, then 2 dots representing a non-bonding pair at the top of the end. Now that's still a complete octet around the N, but now the bond pairs, since that's a possibility of resonance, have such that that bond pair can hop back and forth, and they push each other equally apart, but they're pushed greater by that non-bonding pair, so that this would be a bent arrangement around that nitrogen. On the bottom left, I show the arrangement of another nitrogen bonded in an organic molecule. This is CH3NH2, if you like, to give its empirical formula. The CH3 connected to the N on the left is tetrahedral because there's no non-bonding pairs on the C. 4 bond pairs, they get tetrahedrally apart 3-dimensionally. Then moving to the N, you'll note there are 3 bond pairs, 1 to C, 2 to H's. Then there's a non-bonding pair on the N. This, again, starts out trying to be tetrahedral, but the non-bonding pair takes up 1 location of that tetrahedron. So I have 3 bond pairs, 1 non-bond pair. That is trigonal pyramid. So this molecule has a tetrahedral section to it around the CH3 attached to N, and this molecule has a trigonal pyramid region where you have the NH2 with the N attached thirdly to a C. So we can put a wide variety of various geometries into the locations of organic molecules, depending on, for the C's, there's never going to be any non-bonding pairs, but for other atoms that you functionalize into that connection, there will be possibilities for non-bonding pairs, and you can add bent, really bent, trigonal pyramid type connections into the organic molecule. Let's look at some of our VSEPR ideas for organic molecules. Now, organic molecules with carbon, of course, and we'll think of the blue as carbon and the white ones as hydrogens. So this is the simplest possible hydrocarbon molecule, which would be CH4. No non-bonding pairs on the central C, 4 single bonds outward to the H's. The 4 bond pairs push as far apart as they can, and you get a nice tetrahedral arrangement around the central atom of 109.5 degree 3-dimensional bond angles. Now, if I have a second methane molecule, which of course is a tetrahedral molecule as well, and I allow them to react together, what I can do is remove one of the CH bonds from one and remove an H from the other, then attach the 2 bonds with, I end up with a double tetrahedral molecule. tetrahedral on this end, tetrahedral on this one. I called it CH3, CH3, which is ethane. So this is the ethane molecule, which is concatenated three-dimensional tetrahedral centers. If I went to propane, I'd pop another H off of one location, slide another methyl on there. I'd have three concatenated tetrahedra. Butane, 4 concatenated. Pentane, 5 concatenated tetrahedra. And then on it goes. Octane is 8 concatenated tetrahedral arrangements around 8 individual central carbon atoms. Okay, now what I can do is maybe look at something a little more complex. This is a hydrocarbon molecule that has a double bond section between 2 of the carbons, and it has a single bond section between 2 hydrocarbons. Notice there are 4 connections around this carbon. They push as far apart as they can. This region of the molecule is tetrahedral. Around this carbon, there's 3 attached bonds. There's a hydrogen bonded at the bottom. There's a double bonded C here, and there's a single bonded C here. And remember, these 2 double and single bonds, or these 2 single and 1 double bonds, do not make differences to the repulsion in the VSEPR theory. So these are all 120-degree angles. This C up here has 3 things attached to it. A double bond to a carbon and 2 single bonds to hydrogens. These angles are 120 degrees. So this is a planar arrangement around this particular carbon, and there's 3 bonds as far apart as they can. That would be what we call trigonal planar in that section of the molecule. Now, then if I take an even more complex arrangement of connections of atoms here. Now, let's go through this and look at the various kinds of bonding region that appear in this organic molecule. First, here in the center, I have a carbon-carbon triple bond between these 2 carbons. Then I have a single bond outward from that. These sets of pairs get as far apart as they can. So around the carbon-carbon triple bond, there's a linear arrangement to the single bond that's attached for the remaining location. Remember, this carbon has a complete octet. This carbon has a complete octet. So there are a total of 4 bond pairs around it with no non-bond pairs. This triple bond pushes 180 degrees apart from this single bond. So that is a so-called linear region of the molecule. Then we turn to this section where I see a carbon here that has 3 things attached, a single bond, and a double bond around this carbon. So that would be a trigonal planar arrangement around this particular carbon. Here's another trigonal planar arrangement around this connection. Here you see a double bond, 2 single bonds. Now out on this side, what I'm showing is a bond, but 1 lone pair. So I have a single bond to this atom, and a non-bonding pair of electrons on that atom. This is a trigonal pyramid section of the molecule in that location. Then finally over here, what I see is this red sphere has a single bond, and 2 non-bonding pairs of electrons. 2 bond pairs, 2 non-bond pairs. This particular region is a a really bent section of the molecule. 2 bond pairs, 2 non-bond pairs, really bent location around that part of the molecule. So when you start putting all these various aspects of geometry together, you can get the complex geometry of a huge collection of carbon atoms put together to make some really elaborate protein type molecule, some enzyme type molecule or something like that. Then finally, let me show you one of my favorite molecules of all. That would be this molecule. Look how cute this molecule is. It's got this tetrahedral region back here and a tetrahedral region here and a really bent region here. This represents CH3, CH2OH, and this would be the structure of ethyl alcohol or ethanol. Again, tetrahedral, tetrahedral, really bent region. And if you look at it really cute, look at how cute it is, it looks like a nice little puppy dog. So I have this puppy dog arrangement of the atoms in my ethanol molecule. So that's a little tour of the way organic molecules can begin to form their very complex structures.